So another way to find the delta H of the equation is to look at the bonds that is either forming or breaking. So here are the knowns. So we know that the bond carbon with hydrogen is either required 413 to break it, or you're going to get 413 when you make it. And the same is for the following. And here in this reaction, things are breaking and reforming. So what we're going to do is how much energy to break every bond, and then how much energy to form every bond. And then if we take a look at the difference, then we can figure out what the delta H is. The hardest part about these problems is to really figure out what the Lewis structure is. So for something like Cl, it's pretty easy because there's only two objects. But something like CBr3H, you'll be tempted to do certain things. Now, the best way to look at it is look at the valence electrons. So carbon has 4, bromine has 7, and then hydrogen has 1. So most likely the thing is going to be the carbon. Also, another way is looking at the least electronegative, which is carbon. So carbon, it will be my center. And then I have bromine, 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 and then hydrogen. So that makes the most sense to kind of make a compound. And like I said, because bromine, bromine, bromine all can only do one bond. Hydrogen can only do one bond. And carbon could do 4 because it has 4 valence electrons. Chlorine also has 7, so that means it's going to make one bond with itself. And then here you have almost the same thing, but instead of hydrogen, you have chlorine. So it's practically the same thing, but instead of a hydrogen at the end, it's going to be a chlorine. In HCl, there's only one of each. So here is my Lewis structures of all of them. I did exclude the lone pairs just to make it a little bit cleaner, but that's what it is. Now, what you want to do is just look on the left side, look at all the different bonds you have. So I have a CBr bond, and I have 1, 2, 3 of them. I have 1 CH bond, and then I have 1 chlorine-chlorine bond. So those are my bonds. So if I put this together, so this is going to be equal to my energies. I'm going to look right here. Carbon and bromine. Oh, it's not even here. Uh-oh. So how do we solve this? Don't worry about it. Let's see. Is there anywhere? Carbon, bromine? Nope. No carbon, bromine. All right. And what I mean by don't worry about it is when we get on to the other side. Let's just skip there so you don't freak out. So here you'll notice you have carbon, bromine. And you also have 1, 2, 3 of them. You have carbon-carbon, or carbon-chlorine. And there's one of those, and that's going to equal carbon-chlorine is going to be 328. And then you have a hydrogen and chlorine, which is 431. Now, the reason why we don't have to worry about it, notice on the left and the right, they have the same bonds. And when you look at the structure, these bonds technically don't break. The only ones that do break is this one and this one. So we're only really looking at that. So when you're unsure, you can always write it out, but if you see it on both sides, that means it's not going to break. So you can kind of ignore it. In this case, we're kind of forced to ignore it because we don't even know the quantity. So since it's on both sides, we can cross it out. Let me go back, fill these. CH is 413. ClCl is 242. All right, let's add them up correctly. Here we're breaking bonds. So if we're breaking bonds, the delta H is going to be positive. To break bonds, we're going to input energy. So it's going to be positive 413, positive 242. So add those together. 413 plus 242. Shoot. 413 plus 242, and that is 655. Here we're making bonds that we're going to gain energy, so it'll be negative, and you add those together, 328 and 431, and I get negative 759. Okay, so now you just look at both sides and you add them together, positive and negative. So my final delta H is equal to negative 104 kilojoules. So that's it. Look at everything. You could technically break every bonds, but if you see them both the right and left, meaning that they did not get broken, you could just ignore those and just focus on the bonds that get broken. For this problem, we're doing the same thing. The hardest part is figuring out the Lewis structure. Carbon dioxide, I think most of us know. is C double bond O, C double bond O. Here we have fluorine by itself, so it's just going to be F2. And in here you have CF4. Now fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. Carbon has 4, so once again it's going to look like a tetrahedral. Carbon's going to have 4 things around it. And then here is another hard one where you have 2 OF. And in this case, it's a little bit hard to figure out, but you kind of know, okay, oxygen only wants to bind with 2 things, fluorine 1, so most likely it's going to look like this. So you have 2 of those. So this is what you have, and then we're going to see what we're going to break. It looks like we're going to break everything. Yeah, nothing's really staying the same. So here we have C double bond O, and then we have 2 of these. So that's going to be 2 times 799. Here we have FF, and we have 4 of these, and that will be 4 times 155. Remember, both of these are going to be positive because we are breaking bonds, so it's going to require energy to break those bonds. So 2 times 799 plus 4 times 155, and it gets me delta H of a positive 2218 kilojoules. Okay, I'm going to do the same thing on the other side. I have 1, 2, 3, 4 CF bonds, and that's going to equal 4 times 485. And now we're forming bonds, so we're going to be exothermic. We're going to gain heat. And then here we have OF bonds. And in this molecule I have 2, but then I have 2 of those. So that's kind of how I represent 2, and then in one molecule I have 2, so total 4. So negative 4 times OF, which is 190. So remember, negative when you're making bonds, positive when you're breaking bonds. So this delta H on the right side is 4 times 485 plus 4 times 190. So we have a delta H of negative 2700 kilojoules. Now take the difference of the two, or the sum. So we get a delta H of this equation, I'll write it up here, negative 482 kilojoules. So this is an exothermic reaction where energy is going to be released, in this case 482 kilojoules per mole. The last problem on CHIP 94 is kind of backwards. You have an equation, so you have NCl3, and it's going to make N2 and Cl2, right? And Cl2, so 3 Cl2s. Okay. And actually, in this case, we actually do have a delta H for the whole reaction. In this case, negative 473. But what we don't know is the bond energy of nitrogen with chlorine. So we can figure it out because we know the left side plus the right side equals the sum. And that's what we're going to do. So on this side, we have, again, drawing the Lewis structure will help the most. Nitrogen has 1, 2, 3, 4, 5 valence electrons. Chlorine has 1, 2, 3, 4, 5, 6, 7. So if you do SNA, you'll find out that they're going to share. Well, let's just do it. So S equals N minus A. So nitrogen wants 8. Chlorine also wants 8. We have a total of 4. So 4 times 8. I could do this. 4 times 8 is 32. Okay, chlorine has 7 times 3, 21 plus 5 is 26. So that will give me 6. So they're going to share 3 bonds, or have 3 bonds. So the Lewis structure for this will be N, Cl, Cl, Cl. So a trigonal planar. And this is going to make N triple bond N, and then Cl, Cl. Okay, so these are my Lewis structures. Then I'm going to find out how many of each. So N, Cl, and I have 1, 2, 3 of them per molecule, but I also have 2 molecules. So 2 times 3 times this one. Now this is unknown, so I'm just going to make it X. So 2 times 3 is 6X. So that's the left side. So delta H on the left side is positive 6X. Now I'm actually going to drop the positive because I want the negative to be on my answer, or positive. In this case, it's going to be here. So I'm not going to worry about it till the end. On this one, I have N triple bond, so that is 942. and I have one of these. And remember, this is negative because we're forming a bond. We have Cl-Cl bonds. In this case, we have 3 of them. So negative 3 times 240. I'm going to add this together. 942. 3 times 240. And I get negative 1662. So I know 6x plus negative 1662 is going to give me negative 467. And that's how we solve. We're going to solve for x. So I move this to the other side. So 6x is equal to 1195, then divided by 6. And I get about 199.2 kilojoules. Now, sig figs, am I okay? They're all 3, so I'm just going to make it 199. So that's how you do it. Same concept, but this time the unknown isn't the final delta H. It's actually one of the bond ones. But you're going with the same thing. Positive on the left because you're breaking bonds. Negative on the right because you're forming bonds. Add the sum together to get the final. So this is the last problem on CHIP 94.